graph next part is a graph spectral analysis. So, this can be done with the Laplacian matrix. So graph spectral analysis is something like consider the eigenvalues of graphs, like what we did for matrices. For example, if this is an adjacency matrix from this graph, then we define a Laplacian matrix as this L. Laplacian matrix L, which is D minus, which is defined as D minus A. Here the D means a degree matrix. Here the edge 1 has a degree 1 to 3, and 2 has a degree what? 2 has a degree 2, and 3 has a degree 2, and 4 has a degree 2, and 5 has a degree 1, something like this. So from this degree matrix, subtract the adjacency matrix from a degree matrix of the graph, then the Laplacian matrix is defined. So now we have a Laplacian matrix L like this from the graph. Eigenvalues and eigenvectors, yeah, you know what the definition of these eigenvalues and eigenvectors, how to find it. We can find the eigenvalues of this matrix by using the characteristic polynomial, and we can find the corresponding eigenvector by solving the linear system of equation like this. And we can do it by hand, but also we can use many possible available tools to compute this. And we are trying to consider the eigenvalues and eigenvectors on Laplacian matrix. There are many possible the researches on this. Actually, these are the examples that I draw from papers, recent papers in chemistry. A spectra obtained from adjacency matrix of a metal cyclobutane shown in graph here, and this is a adjacency matrix, and this spectra means the eigenvalues. And nodes 1 and 3 has 3 edges. Nodes 2 has 2, 3, and 3 and 4 edges has nodes 2, 3, and 4 has 2 edges, and and nodes 5 has only 1 edges. The magnitude of the vector component of the largest eigenvalue of the adjacency matrix reflect these observations. Okay. From the eigenvalue of this matrix, we can find the meaningful information of this graph. And this is what this data shows it. This is a Laplacian matrix of this. This table shows the spectra obtained from Laplacian matrix of same methyl cyclobutane shown in the graph. Okay. Here, the nodes 1 has 3 edges, and nodes 2, 3, 4 has 2 edges each, and nodes 5 has only 1 edge. Also, the magnitude of vector component of the largest eigenvalue of the Laplacian matrix reflects these observations. So now we have two tools. Sometimes this adjacency matrix is enough, but sometimes the analysis on this Laplacian matrix gives better information from the given graph. The largest eigenvalue, LEV, depends upon the highest degree in the graphs. Largest eigenvalue depends on the highest degree in the graph, the vertices. For any k regular graph G, the eigenvalue with the largest absolute value is k. The corollary to this theorem is that the largest eigenvalue of a clique of n vertices is n minus 1. And in a general connected graph, the largest eigenvalue is always less than or equal to the largest degree in the graph. In a graph with n vertices, the absolute value of largest eigenvalue decreases as the degree of vertices decreases. And the largest eigenvalue of a clique with 11 vertices is 10, and that of a linear chain with 11 vertices is 1.932. These are the kind of the fact that was already studied and is used in the research in those examples in chemistry. Okay, this is an example of chain, the linear chain with 11 vertices. This is a graph. So also we can think of the adjacency matrix and Laplacian matrix. And the giant component of reaction network, we call it, can be found from the web resources. Here, the blue represents nodes belonging to the giant component, and green nodes representing reflections and reactions of glycolic acid pathway in the giant component, and red nodes belonging to other clusters. So those, actually these are the real examples. And this is tuberculosis, and this is from Laplace. So from these graphs, when we analyze it, those graph theoretical techniques could be used, and those results was shared in the papers in chemistry. Giant component of the reaction network of M. tuberculosis and M. Laplace. Here, this is a Mycobacterium Laplace, or is also known as Hansen's coccus spirale. And this 한센병에 관한 거, 투베르클린 결핵에 관한 거고요. Okay. Anyway, so so these are the kind of the example that the matrix theory and graph theory were used in analyzing the problems in other than mathematics. Here, the analysis of subclusters in the giant component. The graph spectral analysis was performed to detect subclusters of reactions in the giant component. To obtain the eigenvalue spectra of the graph, the adjacency matrix of the graph is converted to a Laplacian matrix L by the equation L is equal to D minus A, degree matrix minus adjacency matrix, where D is the degree matrix of the graph, is a diagonal matrix in which the ith element of the diagonal is equal to the number of connections that the ith node makes in the graph. It is observed that reactions belonging to fatty acid biosynthesis and the fatty acid synthesis, two cycle of glycolic acid pathway in M. The tuberculous form, M tuberculous form distinct, tightly connected subclusters. And this is the reference that I used to explain this graph partitioning algorithms and Laplacian eigenvalues. I think Xun Xiao is have recently working on this subject to work. And this is some examples. The patent big data analysis using graph theory, which was published in Advanced Science and Technology Letters in 2015. And this used this kind of graph theoretical analysis for big data analysis. And correlation coefficient matrix of 5 vertices was used. Connecting graph theory and big data. This comes from this website. Using graph theory, many networks can be described simply by nodes and edges connecting those nodes. Graph theory facilitates much of network analysis, including such algorithm development as the greedy algorithm or page rank algorithm. Graph theory, an often abstract math usually associated with combinatorics, can also be applied practically to concisely and visually represent a network. One basic analysis using graph theory is the prediction of new edges, relationship, bonds, connections, etc. The algorithm is quite simple. Choose the lowest degree nodes and notice the nodes that are 2 edges lengths away. Then the new edge will be created between the lowest degree nodes of one component and the highest degree nodes of a distance 2 away from the original node. Those are the kind of things that were found in the earlier paper that I showed you. And also recently, not only graph theory, the topological approach was used for the big data, which is called topological data analysis, TDA. TDA is also do the same thing. It is a more advanced mathematics from a subject on topology and to visualize the big data in a meaningful way, which is now quite attracted by many companies. So these are the kind of the graph theory which can be used in big data research. Okay, so I think that's the end of the Laplacian matrix. So you just go back to what has been covered and summarize what you have understand and raise your questions for the specified subject that you have interest. I think that's it. So we have covered most of mathematics so far. So we will start the big data and data mining by using the computational skills from the mathematics. Okay, and this is not this. Okay. Anyway, we will meet on next Tuesday here to go through the review of the predictions that we have left, and then we will continue the presentation of the contents from the big data and machine learning. Any questions? A comment?